Hello everyone. Hi. So please, everyone takes your seat because we're gonna start in a few.
Yes. So welcome guys. Before we begin, and where's the clicker? Thank you. I wanted to tell you guys about something that's happening this weekend. I'm one of the Techstars Startup Weekend organizers, and we put together a special hackathon based on AI because we have this amazing community of learners, enthusiasts, master students, PhD students, business people interested in AI. Now the thing is that when we got people coming in yesterday, they were like, we're not really sure what Techstars Startup Weekend is. And this was amazing because everybody's interested. AI is something that's buzzing and it's trending and it's very cool. But the people in the room behind you, they decided to participate. They decided to give up their weekend, spend $20 on something that they don't really know what it is and what's going to happen. So I just want to, if you guys just give a big round of applause, and they won't know what it's about, but this is for those guys that have the courage to actually do something and take part in this. And I'm just going to take a couple of minutes just to tell you about what they're doing this weekend. So Startup Weekend, it's a community-driven event. It's to actually get new people to engage in entrepreneurship, to come to learn, to meet each other, to build out their networks, be creative, come up with ideas. Techstars is a global brand. So this event is taking place in many cities around the world since its inception, and we have many community organizers, something that just went all over the world. So what actually takes place in a Startup Weekend? You get a chance to connect, get to meet new people, share your ideas. What do you think? So you've been learning stuff, but what is that making you think of? What are you passionate about? What's happening in society right now, in your community, in your environments? What are the problems around you? And then all these tools and techniques and things you're learning, how is it relevant? What can you build with this? And so we want to take you on this entrepreneurship journey. What do you discover? What can you learn? But the most important thing is to start. Starting, it doesn't have to be perfect. It doesn't have to be, I don't know, like, so, okay. Let's go through the week, what actually happens in the event itself, and then we'll come back to this. So yesterday, the guys in this room, they came together, they got to meet each other. We had dinner, we had snacks, we had some fun games. Then they came up and they started pitching their ideas. Whatever this is that they felt, they went ahead and they pitched it. Based on these ideas, they chose, based on themselves, they chose to form teams. Which idea they liked, which ones they wanted to be part on. And then they started building a team. Today, they take that idea, they did some research overnight, and now we've had a series of workshops where they really went deeper into understanding what it is that they're doing. We're giving them mentors, we're giving them all the different gaps that you need to actually create a business. Tomorrow, they're going to be presenting in front of a panel of judges, so they've been working non-stop since yesterday. You guys are invited to come tomorrow as well and attend. It's from 3 till 6 p.m. as well, to see how everyone has done. What have they been working on? What have they come up with? To support them, to show that you appreciate what's going on. So that's Startup Weekend. We're doing a special AI edition. Part of the purpose, this is very similar to what Beirut AI community is about. It's about engaging together. We're living in the MENA region, we're in Beirut. But actually we have the opportunity to connect and all learn together. This is something that is more possible than ever, and Beirut AI is connected to all the different cities, which Christophe is going to introduce in a second. So that's what's happening right now. Startup Weekend AI is taking place in 14 other cities around the world, from Hong Kong, Bolivia, Lima, Peru, Montreal, Paris, Brussels, Turkey, Jeddah, many different cities. And we were able to bring this event here today because of our support and our sponsors from these guys above. So another round of applause for these guys. Just one more thing about what we did differently in this event. This morning, the teams have been going through workshops. So instead of just taking their idea, we've put them through a special track. And these are workshops, these are boot camps. It's all about learning. It's actually not about the idea. The idea is just something that you believe in, but everything you learn on the way, that's what you benefit from. All the conversations you have, everybody that you meet, this is where you really go. So we took them through a design thinking process. Think about the problem. What's happening in your community? And this actually helped people stop being so focused on their one idea and started thinking around it. And this is where you find innovation. So the next part of it was about the business model. Okay, great, you came up with an idea, it works, I can see customers, but is it innovative? Is it something that's really going to challenge and change things? Actually, I think George is still working on the last bits of his presentation. This is about community building, actually. So once you have a product, how are you going to engage and find people that are going to give you the validation that you need to see if this works? One of the benefits of it is that you get the global mentor. So we have a number of global mentors that are coming in and supporting us through Skype calls. Here's the thing, Startup Weekend is not about cash prizes. This is not really important because what we have instead is this huge network, and the teams that are participating today, they're going to get fast-tracked to Next.AI. It's an accelerator based in Montreal and Toronto. It's the leading accelerator for AI. So if they have an idea, not even the prototype, just an idea that makes sense, that has an application for AI, they have a chance to take it to the #1 accelerator and get accepted so they can start building that with a team around them. And Canada is investing a lot in AI. The top winning team out of all the teams globally, the top 3, sorry, gets a chance to fly to the Startup Weekend AI Summit next year in Paris. And for all the startups, they get Google perks, F6X perks, and they're going to be part of this online incubator where they get access to these mentors. So let's see if we can play this quick video. Maybe not.
Techstars is a global ecosystem that empowers entrepreneurs to bring new technologies to market wherever they choose to build their business. Our ecosystem includes founders, alumni, mentors, community leaders, investors, sponsors, and many more. We run accelerators all over the world in different vertical markets.
One of the big visions of Techstars is being able to support entrepreneurs at every stage. Startup programs for Techstars are a reflection of the early stage events, supporting entrepreneurs really at the grassroots community level.
Startup Week is a celebration of entrepreneurs in cities around the globe. Startup Digest is a personalized newsletter for all things startup around the world.
It's about helping entrepreneurs get their start. Startup Weekend is really the best launching point into programs like accelerators. Techstars obviously is really investing in communities and ecosystems.
We all have a drive to create something new. Startup Weekend's that opportunity for you to express that.
There are people in rooms like this in places all over the world learning the same things, experiencing the same things, and I hope that's inspiring for you.
To date at Startup Weekend events, we've had more than 100,000 attendees, over 23,000 something companies, over 140 countries.
You get to meet a lot of cool people from all over the place, and you get to feel that entrepreneur energy.
Since the weekend, I've actually kept in touch with a few people from my team and also managed to leverage the networks of the people I met that weekend to meet others in the startup community.
My favorite thing about Startup Weekend is just how human it is. We have built a platform that really gets to connect communities around real problems, real people, real ideas. This is a journey. It is a life choice that, it's not easy, but we can help guide people through.
Okay, so a quick reason I showed you that video was because what we're doing today actually is creating video content that can tell the story about what's happening here in Beirut, which is about you guys and the guys in that room. And so we're just going to be we're following the whole entrepreneurship journey, and we want to explain to people why they need to engage in this way, why this is something for you guys, this is exciting, this is something you can do. So we might grab you, we might do some interviews and some videos, you see a lot of different cameras around. We want to share this story. We want to get entrepreneurship as something that everyone has this mindset, everyone is creative, everyone is working on something. And so that's what we're here to do. Again, it's all about starting something. If you're working on ideas, think about how you can take it forward. And next time, think about participating. It might be fun. Also, one of our co-organizers, Ala Marouf, she's been super busy juggling many different things. I'm going to give the stage back to her. Do you want to come with the steps? It's a little bit easier. Thanks, guys.
Thank you. Hello, everyone. Thank you for coming here. And now we'll start with our Beirut AI gathering. So, a bit about us. Beirut AI is a local community in Lebanon. So we are part of a global community called City.AI. Our goal is to get people on hands-on AI, and that means we want communities, startups, individuals to understand the concepts of AI and give them all the tools to be able to also apply it. Through several events, workshops, during the workshops we have like almost monthly workshops where people get a glimpse of the theory and they can also apply it right away through coding. And we have quarterly gatherings like this one where we get AI practitioners from the field to share their experiences. Okay. It's not working. Okay, so as I mentioned earlier, we are part of a global community called City.AI, where it has communities from all over the world in over 50 countries and cities. And this enables us to achieve our goal not only on the local level and connect AI practitioners on the local level, but also with AI practitioners all over the world. We would definitely like to thank our partners, NAR and BDD, for hosting us and make this event happen. Before starting our event, I would like to invite Mr. Rami to talk about the Syndicate of Computer Sciences in Lebanon. Go ahead.
Thank you. I'm going to talk in Arabic. Is that okay? لأنه أغلبية الأشياء المعلومات باللغة العربية. أول شيء لأعرفكم عن حالي أنا مين؟ رامي سنتينا، حاليا رئيس نقابة العلوم المعلوماتية بلبنان. تأسست بماي 2018 بقرار من وزير العمل. حاليا أنا بشتغل as a head of graphics development بشركة CCT. عادة presentations بيكونوا technical بعملهم، فهالفترة أول فترة بصير عم بحكي أشياء قانونية شوي فتعودت. أوكي. So النقابة هي انعملت لكل الخريجين اللي عاملين computer sciences، يعني MIS, computer science, business computing, bioinformatics, the list grows. فمن كل الجامعات بلبنان أو اللي بتعادل الشهادات بالجامعات اللبنانية، يعني من وزارة التربية. فالمسار القانوني بلش الشغل عليها من 2017 من مجموعة أشخاص. ب 26 أبريل أخذنا الترخيص ومشينا بالمسار التأسيسي. لا صار المساعدة على النظام الداخلي وقانون النقابة ب 3 أغسطس، وبسبتمبر أوائل سبتمبر أخذنا إذن مزاولة العمل النقابي من وزارة المالية. هون ببلش العمل النقابي صار مفتوح لنا completely. من وقتها بلشنا زيارات على الجامعات، بلشنا نحكي مع الجامعات، وكل الجامعات صاروا يا عم بيفوتوا يا عم بيحضروا وراءهم ليفوتوا، وفي كتير فاتوا already كأساتذة كفاكولتي ممبرز وكهذا. وهلا بلشنا to outreach communities، ومنها الكوميونتي بيروت AI، وهوبفلي يكون في تعاون كبير مستقبليا معهم. هلا احكي شوي قوانين. قانون النقابة، قانون النقابة هو أهم شيء. يعني في كتير ناس بيسألوا شو التقديمات النقابة. هو الأهم التقديمات أكيد جاي وفي كتير بلشوا يجوا، بس الأهم هو القانون تاعه. قانون نقابة العلوم المعلوماتية قريب على قانون نقابة طالعة من مجلس النواب، بمعنى الشهادة الجامعية هي الأساس. إذا معك شهادة جامعية بالاختصاصات تبع النقابة بحق لك تفوت، وما بحق لمجلس النقابة يرفض طلب انتسابك. قوانينا فيها استفدنا كتير من الخبرات الموجودة بالنقابات الموجودة قبل، مثل نقابة المهندسين، نقابة الأطباء، المحامين وكتير غيرهم، صيادلة أكتر شيء كمان. وبمعنى لنخفف الفساد اللي معقول يصير مستقبليا. انا هلا حاليا رئيس، بس بعدين رح نعمل انتخابات اكيد مبكره للكل يتمثل بالنقابه، فما حكون موجود. فبس شو الضمانات اللي بنضمنها للمستقبل؟ النقابه عم بيصير فيها اموال، كيف بدنا نضمن عدم الهدر بالنقابه؟ فاللي عملناه هو خلصنا خففنا صلاحيات الرئيس حطيناها بالمجلس، وصلاحيات المجلس شلناها حطيناها بالهيئة العامة. المجلس النقابي بحق له يصرف 25% بس من مدخول النقابي السنوي، يعني ما في يجي يلاقي بناية حلوة حد البي هون نشتريها ونقول هذا مركز النقابي. بدنا نرجع للهيئة العامة. الهيئة العامة هي كل المنتسبين بقلب النقابة. الايميل is a legal way of communication بين كل الأعضاء. هذا قبل القانون اللي طلع من مجلس النواب. شو اسمه في اشياء كتير بتصير بالنقابات. رح احكي بس عن نقطة واحدة مهمة، هي كيف بتصير الهيئة العامة. نحن قوانيننا كتير صارمة خاصة بقصة الأموال، بس بعدين بتجي بيغيروا له. يعني إذا كان بصير حبر على ورق، يعني اللي بيصير هو الهيئة العامة تدعى بدعوة بتنحط على باب النقابة حسب قانون تشريع الأعمال النقابية قبل 15 يوم من الجلسة. الجلسة بتصير بمن حضر، إذا ما كان في شو اسمه نصاب قانوني ب 15 يوم، بعد 5 أيام بتصير بمن حضر. فبتغير العالم، بتغير اللي بدها إياه، لأنه ما حدا بيمرق على النقابة بيشوف شو في أعمال، شو في دعوات لاجتماعات. فاللي بيصير اللي نحن عملناه إنه مجبور رئيس النقابة يبعث باي إيميل لكل الأعضاء تاريخ وجدول أعمال الجلسة قبل 15 يوم. هيك كل العالم بتصير بتعرف، هيدي الضمانة لكل العالم تعرف شو عم بيصير وتنزل تشارك بالأعمال النقابية. اوكي. بنفتس مثل كل النقابات الكبرى، وشوي شوي عم نصير كبرى. فاميلي انشورنس، يعني انشورنس للأهل، للأشخاص، لأولادهم. أهم شيء عالم أكثر شيء بيفكروا خصوصا إذا ستارت ابس وهيك إنه بدي انشورنس لعائلتي، لأهلي الكبار بالعمر أكبر مني. مع النقابة أكيد هيدا حيكون موجود، و during ديسمبر حتطلع الجداول أونلاين على الويب سايت تاع النقابة. retirement salary بتصير بعد X amount of years بالنقابة، بعد الهيئة العامة بتقرر بس تمرق سنة مالية على النقابة لنشوف شو مدخول النقابة السنوي، قد ايه بيكون retirement salary وشو قوانين retirement بالنقابة. legal support هذا شيء طبيعي بيكون بقلب النقابات. training seminars workshops حيكونوا بقلب النقابة بالتعاون مع النقابة مع الجامعات والانستيتيوتس اللي موجودة. وقريبا حيبين كل شيء حنعلنه اونلاين، شو الديلز اللي عم تنعمل بخصوص هالموضوع. واكيد ديسكاونتس وكثير اشياء عم تطلع، يعني ديسكاونتس من الانستيتيوتس على مثل كورسات مايكروسوفت والسيرتيفيكتس اللي بيعملوا الواحد بعد ما يتخرج ويستفيد منهم. فبيكون في ديسكاونت كبير لاعضاء النقابه. الابلكيشن اتس اونلاين، تشيك اور ويب سايت SCSL.org.lb. مش رح فوت احسن ما اطول عليكم كثير. اوكي. و اتس ايزي، the process is easy بس اتس ليجل، سو في اوراق كثير واحد يجيبها بتاخذ وقت، من السجل العدلي، مساعدة على الشهاده من وزاره التربيه، وبيتقدم الطلب يلي بنبوست يعبر النقابه. ثانك يو. Do I have time for questions? Is that free? Yeah. أكيد نحن كنا من كم يوم كنا عند فخامة الرئيس الجمهورية وكنا بنحكي بهالمواضيع كلها. الفكرة نحن عم نجمع كل العالم، عم نجمع كل الاختصاصات اللي بقلب هالدومين، ومنها حيطلع مشاريع قوانين على كل شيء تنظيم للمهنة. يعني تنظيم المهنة يبلش من الجامعة، من الأساتذة الجامعة للبروفيشنالز اللي صار لهم سنين خبرة، وكل هيدا حيكون من لجان بقلب النقابة. يعني مش انا اللي حاعملها شخصيا بس، ومش رح اقول لك انا شو توجهي، لانه اكيد عندي راي بالموضوع انه كيف تنعمل، بس اللجان اللي رح تتاسس بقلب النقابه هي اللي رح تشتغل على الموضوع. فبدعيك إذا مهتم كتير تفضل على النقابة وعلى اللجان بهالموضوع ونحكي سوا. لا أكيد منه مانداتري لأنه نحن نقابة أسست حديثا فما فيها تيجي تحطه إجباري فهو اختياري حيكون وأكيد بس هلا في ناس بتفضله حتكون في ناس بتقول لا إنه حسب إذا هو مع شركته يمكن بده يعمل انشورنس لأهله فبيعملها كمان. لا اختياري فبيكون زيادة يعني هلا نحن 300,000 هو الاشتراك السنوي والانشورنس بتدفعه لحاله إذا بدك.
Thank you so much.
Thank you.
Thank you, Rami, for the very nice presentation and the information. Okay, so today we have a very rich AI schedule, and we're going to have talks from practitioners in various topics, from recommender systems to medicine to music. Our first speaker is Mr. Ramzi, who is a senior developer at Anghami, and he's going to share with us more about Anghami and the recommender system.
Thanks. So, hi everyone. So I'm a senior software engineer as part of the machine learning team at Anghami. And I work specifically on recommender systems. And today I'd like to just give you a high-level overview of the whole process of our recommendations infrastructure. So how we go from data to machine learning models and then to serving those recommendations. So this doesn't seem to be, okay. But before we do anything, I'd like to just give some context. So Anghami is 70 million users, and those users have access to 30 million songs. But the interesting part is that every day those users listen to about 100 years worth of music, and that's a lot. It's not just a lot. It's not just a nice number. What this means is that this gives us a lot of training data to train machine learning models that understand user tastes and can improve over time. So why are recommendations such an important part for us? Well, because they're pretty much everywhere. So you might think about recommendation systems as being, here's a playlist that you should listen to at this moment. But actually, recommendation systems go much deeper into some of the features of our product. So one area that you might not think about is how we order the friends such that you have the people with the same music taste first rather than at the end. And if we look at the trend over time, the plays that come from recommendations over overall plays is actually going up. And so over time, the importance of our recommendation systems is only increasing. So what are those recommendation systems? Well, you can think about recommendation systems into two broad categories. You have collaborative filtering systems on one hand, and those are systems that really take into account previous interactions between users and items. And thank you. And they base the recommendations on those previous interactions. On the other hand, you have the content-based recommendation systems, and those don't look at the interactions between users and items, but rather at the content itself. So what are the features of that content? What are the audio? What does the audio sound like? What are the images? The metadata. And one thing I'd like to note is that those aren't totally separate areas. We see a lot of content-based features that go into the training of some collaborative filtering systems. So I'm going to start with collaborative filtering systems. The general idea, just the basics, is that if you have a user 1 who likes items A and B, and you have a user 2 who likes items A, B, and C, then it's very likely that user 1 will also be interested in item C. versus any other random item. And that's an oversimplification, but once you have a lot of those users and circles that are overlapping in taste, you start getting some pretty interesting co-occurrence patterns that you can detect. The first algorithm we use is matrix factorization. And those of you who have worked a bit with recommender systems have probably heard about this. It's one of the classical examples, algorithms used. So basically what we're trying to do in this case is we have this very sparse matrix of interactions between users and items. And what I mean by sparse is that we have users on one hand and items on the other. But since we have millions of songs, each individual user has probably just interacted with a tiny fraction of those items. And so what matrix factorization does is it takes us from this very sparse matrix into two separate matrices that are dense. And so what those matrices give us is a user embedding and an item embedding for users and items. And I'm going to talk about embeddings in a bit. But what you have to understand is that we go from this very sparse problem into something that we can work with for recommendations. And I'm going to explain how we do this in a bit. The second algorithm we use is word2vec. Now, if you're a bit into natural language processing, you have most probably heard about word2vec. Basically, the idea is that we treat a user's cue as a sentence, and every word in that sentence is a song. And so what the problem becomes is, given a song, how do we predict the ones that come next to it in a certain window? And at first, the neural network is not going to get it right, but after we train it on millions and millions of those cues, we start being able to predict very accurate, not very accurately, but accurately to some extent, what other songs should come next to any other. And this is what it looks like. What we're actually interested in is this middle layer, because this is the one that holds embeddings for those items. And again, I'm going to explain what embeddings are in a bit and how we use them. It turns out that collaborative filtering works very, very well in practice. But one of the problems is that if we have a new song by a new artist that we don't know anything about, we can't use the previous interactions to recommend it to anyone. And so we can't really recommend it to put it in any queue or recommend it to any person. And this is where the second type of recommendation systems comes in, which are the content-based ones. So the first content-based recommender system that we use is a deep learning-based one. We use deep convolutional neural networks. We take in the audio file as input, and we try to predict a tag as an output. And after we try to do this on millions of songs, you start... The model has a high-level understanding of what makes up a rock song, or what makes up a pop song, or any other tag in that, for example. And so, again, what we're interested in this case is not actually just predicting that this is a rock song, but we're interested in the layer that comes just before that final classification layer, which gives us a bunch of numbers, embeddings, that represent that song. And the last bit of, the last type of content-based recommender system that we use is a classical, music information retrieval system. This one is a bunch of signal processing algorithms that give us information such as the gender of the singer or the tempo or the likelihood that there's a guitar in that audio file. So I've talked a lot about embeddings. What are those embeddings? Well, you can think about embeddings as a bunch of numbers. But what's special about them is that they're not just some random numbers that represent an item. They have some meaning incorporated in them. And the meaning is that the way the meaning manifests itself is by comparing this embedding with the embeddings of other items. So that's a simple example here. If you have two Fairuz songs, it's very likely that they're going to have the same embedding, not the same one, but very close together, versus a Fairuz song and a Lilisa song that would be very far from each other. And so what those embeddings allow us to do is to take that problem from a high-level sparse matrix or interactions and content-based data and map it to a sort of dense mathematical problem. And this is exactly how we generate our recommendations. So the basic idea is that, I'll give you an example. You start playing a song by Fairuz, okay? What are the other songs that we're gonna give you? Well, we take that number, those embeddings for Fairuz, and we go over all of the other songs that we have, and and then we compare that embedding with all of the others, and we keep the ones that have the highest dot product with that vector. And what this means is that we're keeping the songs that are the most similar to the ones that you chose to play. So just in that case, the Fairuz one would come at the top, whereas Elisa wouldn't be recommended. Just before I go to the next section, so I've talked about the theory of how we generate those recommendations, but it turns out that at scale, it really matters about how we generate those matters. So the way we started doing those recommendations is by running them on a Hadoop cluster that runs on top of Amazon EMR. We have Spark jobs that take in those numbers, compare them to all of the others, and they generate recommendations. Those run daily, weekly, depending on what kind of job it is. But the limitation is that when you have a couple of items, this is fine. But when you have millions of items and you're trying to generate recommendations for them, then a couple of million items times a couple of million others is a couple of trillion items, and that's a lot. That takes a lot of time, and so it's hard to keep those recommendations up to date and fresh, which is why we've recently moved some of our workload towards a live approximate nearest neighbors approach. So we have this custom microservice called Octopus. It's based on top of a library called NMSlib. And what Octopus allows us to do is, besides being cute, is it allows us to answer queries, recommendation queries. So given a set of songs or artists or playlists, Octopus can reply with a set of similar, artists, songs, videos, or whatever you ask of it. So the way this works versus the other is that we're not actually doing the full similarity search. So comparing that vector against all of the others. NMSlib actually pre-builds a sort of index for those, a graph-based index. And that graph-based index allows us to answer queries very fast. So the last thing I'd like to talk about is some of the learnings that we've learned along the way. The first one is start simple. And I know that sounds obvious, and a lot of you would think this way, but it's actually much harder to do in practice. It's sometimes, and we still do the same mistake. It's sometimes very tempting to do the complicated stuff, and that's very true in machine learning. You think that what's complicated is what you need. But what's often truer than this is that if you start with having a simple prototype that you can validate with actual users, then you're going to be able to, then that's actually going to be much more valuable for you. And just a side story here, when we started with the weekly mixtape, which a lot of you are probably familiar with, it was just a bunch of SQL statements strung together. And Spark jobs that we used, they weren't jobs, we used to run those on the Spark shell manually. And so every Monday, my colleague and I would go to the office and between 9 and 10 a.m. we'd run those jobs and update the mixtapes for millions of users. And I remember this one time where there was a lot of traffic on the highway, and none of us could make it in time. And so we started getting complaints from users that their mixtapes weren't updated. And it was just that there was a lot of traffic and we were late to do this manually, and we blamed it on some technical bug at the time. But this actually gets me to my second point, which is it's important to start simple, but it's also equally important to know when you have to invest the time into tooling and abstractions. And so after a couple of months of running this manually, we actually realized that we need to sit down, take some time to build the automation and the monitoring for those for the mixtape. My last point is that you have to be ready to change your opinion, and that's very true for us engineers and product people. We tend to think that we know what users want, and that's a very good thing to have, because you sort of know what you should work on next. But at the end of the day, what decides whether a feature stays or goes is measuring with live users. So if you try to put it out and no one interacts with it, or this is not what users want, then it's something that should go. And that's very true. And I've included the last note. That's very true for machine learning. If you think that just because you have a complex, complicated, deep neural network model, then it should work and people should like it, then you're not going to be presenting a product that people are going to like. No matter how complex your neural network is, people don't care at the end of the day. What they care about is having good recommendations. And if good recommendations means that you're going to have a simple SQL query with some simple code, then that's what it should be. The last thing I'd like to say is none of this would have been possible without the hard work of an amazing team that I'm part of, and without the constant feedback that we get from users. So from all of us, thank you.
No, you can.
Any questions?
Are there features specific?
Yes, please.
Which you get, if you're a pregnant woman, do you have a specific advantage over others?
Yep.
Or is there a specific?
That's actually a good question, and it's actually much harder than you think it is. We do mark in our data which plays come from those recommendation systems with an actual code. So this allows us to track over time the quality of those recommendations. But in some cases we do exclude those from next training loops. But in many cases it's also it's hard to find the balance between including those as feedback, because if you recommend something and people don't like it, you sort of want to know. So you don't fully want to exclude this, and I'm not going to say that we have this figured out. So it is something that we should be working on. But very good question. Yes, please.
2 pregnant women, 2 diabetics.
Yes.
2 people on 2 people on
yes.
whatever condition you want to.
Well, the genre. Yes, go ahead.
If you can bet should be small samples.
He's asking about the part where the deep learning part.
You choose a few. Let's say 5 to 7 or 5.
This one. So in this case, we actually take the frequency bands over time, and we use this to we take this into a model. We predict some tags. Those are depending on the app. We have different versions of this. We have one that predicts genres. We have one that predicts clusters based on other models. But the final the final output we want is not this classification actually, but rather the layer that comes before it. And I don't have a diagram for this model, but we want that embedding layer that comes right before the final classification layer.
Look, and I have an issue with just testing in Lebanon.
Yeah. So what we have is actually I skipped the slide. So we actually use an ensemble of different models. So we have embeddings that come from matrix factorization, MIR, the deep learning model, and we put those all appending them into a single embedding. And depending on the application, we have those shuffled around or with different weights. Yeah, please. Yeah, so this is sort of included in this. In this case, we have some data about the note, the note and the main key of the song. So this goes into this part. So I think you're referring to this part. Yeah. So what we do is not that we're trying to classify that, the Fairuz song, or based on the audio. We're actually doing this on the output of those models, which are embeddings, so numbers that have some semantic meaning. If this comes from the matrix factorization model, that semantic meaning would be, how do people who usually listen to Fairuz, what do people who usually listen to Fairuz listen to next, or next to Fairuz, or in general, depending on which model we're using. And so in those cases, for example, we're not actually looking at the signal or how it sounds like and comparing those. We're comparing some higher level number that represents those songs. Yep. So, for example, in the cases of, for example, in deep learning cases, you have, the classical accuracy measurements and evaluation. But ultimately, what we do to evaluate the performance of our recommendation systems in general is measuring it on live people. So, just as I said a bit ago, we track where you where you got to those songs from. So if we recommended them to you using, a certain algorithm number, we track this, and over time we see, we compare different algorithms, and we see that people who are on algorithm A listen to, 20% more than people who are on algorithm B, and sometimes that's higher than the average, sometimes that's lower, and that allows us to decide whether we should keep this this iteration of the algorithm or not. Yes, please. Yep. So this consideration isn't taken into account in those models, but that's taken into account at the final recommendation. So when you go into your homepage, we recommend some different things depending on the time of day. Do we have any questions? Okay, definitely. So thank you, everyone.
Thank you, Ramzi, for your presentation. Our next speaker is Dr. Joe Tiqli. He is a professor at the Lebanese American University. Actually, he was my professor during my undergraduate studies. He always pushes students to take the extra step to work on projects, and he's also the advisor of the AI Club at LEU. So please go ahead.
Thank you very much. I'm very happy to be here. I was listening to the news as I was driving to Beirut. I live a little far away, and I was a little depressed listening to what's happening in the political arena. And then I got here and I saw Ala. And I saw her glowing face, and I saw Christopher, and I saw Sherbil, and I saw Rami, and I thought, there's a chance for this country. This is the Lebanon that we want. We don't want the silly Lebanon that we see outside or here, not far away from us. We want the tech industry. We want the scientists. We want the people who work objectively to solve problems rather than mess things up. I'm speaking from the heart before I start with the scientific stuff. So thank you for being here. So today's presentation is actually about a project which was developed by one of my graduate students, Ralph Aboud. Ralph is currently doing his PhD studies in the University of Oxford in England. Before he left, we developed this interesting work. He worked on it for about 2 years, 1 year and a half, 2 years almost. It's a framework which composes music. Now, a lot of people ask us about the applications. Why are you building something that composes music? Aren't you replacing human composers? Start with the big question, the elephant in the room. The answer was, we have the privilege of being in academia. We don't need to develop things which have a lot of practical applications. We have this leeway of doing what we want to do. And we wanted to do this. Why? Because we wanted to see how far we can go with AI. Because we want to understand how our own intelligence works. Understanding how our brain works. If we can simulate it using computation, it means we're going farther in our understanding of ourselves. So it's a retrospective search of our inner way of doing or thinking about things. So that was our main motivation behind this work, plus a lot of applications, which we will talk about later. We always have to mention applications, so we'll talk about this later. So the idea was to, okay, let's start with a brief introduction. Composition actually we consider music composition as a human skill. We need human composers to compose music. But actually, some of the big composers like Mozart thought about developing some algorithms to compose music themselves. So this is something that has been in the background for a few years. They were mathematical originally. And then with recent advances in AI, some people started playing with AI to do some composition. So the existing techniques to perform automated music composition, we can organize them in 4 main categories. Translational models, for example, accept as input some patterns. Those could be images, those could be words, we can consider any kind of an input we'd like. And then the trick here is translating those inputs into music. So the innovation part will be in the inputs, and then the translation will allow to transform that input into some kind of a music. Difficulties here, how to produce innovations in the inputs. Is it always easy? And how to translate it correctly or accurately into music. Another approach is mathematical, where we define some state machines or some grammars. And then we try to produce music. Is it me? No, it's not me. And then we've tried to produce some music that follows those grammars or those state machines. The easy thing here, or the beautiful thing with these guys, is that the music will be correct because it follows some predefined grammars or some state machine which rules are predefined, preset. So we're not going to get dissonance, or we're not going to get some bizarre music. But innovation is limited because everything should abide by the grammars or by the state machines that are developed. A third approach is machine learning. So here we go back to part of Ramzi's speech, which has to do with developing neural networks or using other kinds of machine learning approaches to try to compose music based on existing music. So we feed this learner some pieces, and then we tell it, okay, produce something similar to those, but all different. That's the main idea here. And then there's evolutionary approaches, genetic algorithms, evolutionary computation, where the idea is to try to compose music the way nature composes us, the way nature produces organisms, living beings, using the genetic processes of mutation, crossover, and so forth. Now, our own composer, we analyzed the pros and cons of each and every one of the existing techniques, and we came up with a design which is hybrid. We didn't want to compose music just to compose music. We wanted to go a little farther. We wanted to compose music that expresses sentiments. So our objective is tell it what you're feeling and let it compose accordingly. To do that, we needed 2 things. We needed first to train it how to analyze feelings. So it should understand what happiness is in terms of music, what sadness is in terms of music, what surprise is in terms of music. Step number 2, compose music to match those feelings. So for the understanding the feelings part, we used a machine learner. For the composition part, we used a genetic algorithm or an evolutionary algorithm. Regarding the sentiment learner, we can use any learning algorithm can be used. We did not spend a lot of time on really testing different learners. We just wanted to make it work as a first step. So we made some choices based on some aspects which were interesting to us. We wanted it non-parametric. In other words, we wanted it to be free in terms of our own user-chosen parameters. We wanted to work in terms of the music that it learns. So we made choices like that. And then, as any learner, you have to train it, and then you have to start using it for testing. And I'm going to show you a demo a little later in terms of how we train this guy and how we start feeding it music. And it tells us, okay, this piece of music is 20% happiness, 50% sadness, 10% surprise. These are the sentiments expressed in this piece of music. regarding the, to be able to implement a learner, you need some kind of a similarity measure. And you need to process features. And we chose a bunch of features which we thought were interesting in terms of music analysis. Some of them low level, some of them high level. There are many others that could have been considered. We went with the features which we thought are essential, important, but it could be extended to consider other features. Regarding the composer, we followed a not very common genetic approach, or evolutionary approach, which is called Evo-Devo. It starts with very small individuals, which in our case can be considered as the notes, the individual notes, and it starts composing. It starts adding notes together to form chords, and then it starts adding chords together to form bigger and bigger individuals. The traditional genetic algorithmic, or the traditional evolutionary approach, considers individuals of equal size. The chromosome has an equal size, and it duplicates, and it mutates, and it becomes a new chromosome. Here, we're evolving it from a smaller chromosome to a bigger and bigger chromosome. And it'll be as big as the piece of music, right? It'll grow in terms of time length, which means it's growing in terms of chord progressions or the number of notes in the piece. Regarding the evolutionary process, it's not very different from the traditional process where we start with an initial population of basic chords or basic notes, then we mutate and then we cross them together, and then we trim at the end. We remove the useless individuals. We trim based on sentiment expressiveness, so we want these to express the sentiments that we want to express, and we remove them based on repetitiveness. We want variety. We want different pieces every time. So pieces which are very similar, or chunks of pieces which are very similar, we disregard. We kill off, okay? And here we're talking about the mutation operator. To mutate, okay, in biology, mutation means changing the allele expression of a certain gene. In music, what is mutation? We implemented different music theoretic mutation operators. For those of you who know a little bit of music, they know what I'm talking about. For example, try. This is flipping between two notes quickly. This is the try. Staccato. Having the notes played in a disconnected way. Different mutations which allow to transform the music in different ways, right? For the trimming, we spoke about it, so I'm going to skip. So at the end, we got this architecture which consists of 4 main components. We have the learner. We have the composer, which is the genetic process. We have a music theoretic. We need some rules. We don't want to produce music which is incorrect. So we have our music theoretic knowledge base. And we have the feature parser, which allows us to extract all the features that we want to use to train the learner and then to perform the composition. Some parameters that we need to set. We try to minimize the number of parameters because we want it to be as free as possible in terms of our inputs, but there's a minimal number of parameters that we needed to define, like the initial size of the population in terms of the notes or the chord progressions that we start with. Branching factor, size, population size, and fitness, those are specific to the genetic algorithm, so I'll keep them till later in case you have questions about them. Regarding experimental evaluation, maybe it's better to do the demo and then we do the experimental evaluation. Can you help me with that, Christopher? Okay. I'm not a Mac user, so Christopher is going to... Okay, so let me start by demoing the composer. Can you go outside of this? Okay, yes, let's start with the pieces. No, not this one. Go back. The demos. To ring. Okay, piece 1. So wait, before you play. I'm going to make you listen, I'm going to play for you a piece which is a synthetic piece, a piece produced by the composer, and then I'll play another piece which is a real piece, so that you see the difference. Our solution is not perfect, so I'd like to start with that. Please, Chris. So you see, it's a little bizarre, right? It's a little bizarre. It's putting notes together in a bizarre way. Let's play a real piece so that you see the difference. Please, Chris, number 2, yes. So you see the difference. There's a huge difference in terms of the melody, the arrangements, and so forth. Actually, it's the other way around. The first piece was the real piece, and this is the synthetic piece. The first was a modern piece. This is our guy's piece, okay? So it produces music. And let's play the rest of the piece, please, Christopher. Yes, number 2. This was played, let me mention something which is very important. This was played by a human being. The composition is produced by the computer system, but it's not played by a computer system, because when you play it by a computer system, even a real composition will seem synthetic. So we gave all our, when we were doing our tests, and I'm going to talk about this later, we gave synthetic compositions and real compositions to the same musician, to the same pianist. And we told that pianist, please play them the same way. Don't add anything to any of the pieces, because we want to compare. And then we gave those pieces to around 100 participants. Every piece was rated by around 30 participants, and to try to ask them whether they can recognize whether it's real or synthetic, and then rate the sentiments in every piece. This is what we call the Turing test. Trying to ask people whether they can distinguish between the results produced by a computer system or by a human being. And almost, I mean, we got averages which we weren't expecting, like 70–80% of the people confused or considered the pieces to be real, right? We're going to play some other pieces, but let me first show you demos about the prototype system itself. So yes, please. So this is a, no problem. Take your time. We'll show you a quick demo. So this is the composer. We set our target sentiments. What do we want to express? I'm feeling a little bit happy, a little bit sad, a little bit angry, right? Scores between 0 and 100% or 0 and 1. We set some parameters for the genetic composer, and then let me just move a little forward, Chris. And then no, you went very far away. Once we set the parameters, we ask it to compose. We'll click on the composition button, and it will compose. And it will produce a piece like the one you just listened to. It will produce the score, the notes. It will produce the score. And then we gave that score to a musician, and we asked, okay, play it for us. Let's see what we got. Okay? Can we see the other demo? One thing we can do with the... Just one second, Chris. One thing that we can do with this guy is not feed it the sentiments ourselves, but feed it another piece. It could accept as input a piece of music. It will automatically analyze the sentiments using what I'm going to show you right now behind that piece, and then it will compose something similar to the other in terms of sentiments. Not in terms of low-level features, frequencies, notes, pitches, in terms of the sentiments. The older piece, listening, for example, we were talking about Beirut songs. Beirut songs usually reflect maybe nostalgia or love or, I don't know, joy. So I want another piece which reflects the same sentiments. Okay, it might be a piece by a Spanish composer or a South American composer, right? It's going to process the sentiments. So here the sentiment analyzer takes as input a bunch of pieces. It takes as input a bunch of, we want to train it first, so we give it a bunch of pieces as input with the sentiments that people who listened to those pieces before labeled, right? It should learn how human beings perceive music. So that's the first step. We try to match the low-level features with the sentiment scores of the humans. We train it, and then after that, it starts accepting new pieces and providing us with the sentiments expressed with those pieces. Can you augment the volume, please, Chris? So we're going to test with one piece. It's listening to the piece and it's analyzing. Fear, anger, sadness, surprise. those were the ratings. Of course, it's a percentage. We're gonna try with another piece. This guy is a little angry, sad. Let's try with another piece which is slightly different. Silent Night. All of us know Silent Night. What does it reflect? Happiness, joy, peacefulness. Let's see. Joy and love. Right? This is Silent Night. So this is how it accepts the piece after learning, and it produces the sentiments accordingly. Let's see some of the sentiment pieces. Yes. Let's go with anyone. Okay, this is the same. We trained it on pieces which are more complex. For example, yes. This is the older Kalaminas program, right? It's a complex piece in terms of sentiments. It has happiness, it has sadness, it has surprise, and our guy fairly detected that. In other words, when testing, it was able to detect this complexity in terms of the sentiments. Some people ask us about, I'm sorry, Chris. Some people ask us about where are we? Whether it produces pieces which are diverse or whether the pieces are very similar. I'm going to make you listen to the beginnings of some pieces that it produced. So here, let's. This is one. Can we change the piece, please? That's oh, yes, 30. Another piece. Synthetic. Right? All synthetic. This is another synthetic. Now at the end we thought, okay, we want to, this guy seems romantic in its style, a little classic, a little romantic, the composer. So let's try to tweak some of the parameters to make it change its style. So we went with something which we call the crazy piece. So you see it's diverse, it produces diverse music, it produces music that express sentiments fairly accurately. We did some tests, obviously. This is a research work. It was published in the IEEE World Congress on Services, which was organized in San Francisco this summer, and it's submitted for publication in the #1 journal in its area. International Journal, if I remember, of Soft Computing and Applications. So we had to do a lot of tests to make sure that it's working properly and to make sure to try to analyze how it works. So the learner was evaluated in terms of the size of the training set, in terms of the number of neighbors that we're considering. We worked with a fuzzy KNN learner. We analyzed the sentiments separately to see which sentiments are more complicated to analyze or predict than others. We saw that, for example, joy and sadness, which are very generic sentiments, are easier. They are more resistant to noise than other sentiments, which where accuracy tends to decrease as a little more noise is included in their neighborhood when the decision making is being evaluated. Regarding the Turing tests, as I explained very briefly a couple of minutes ago, we asked people to rate the pieces, human, non-human, and then we tried to chart those, and we tested with real and synthetic pieces. The testers did not know about this, of course. We knew about them. And so we we were able to pass the Turing test, if you want, with flying colors. We weren't expecting this much of a, because passing the Turing test means confusion. We not only confused, but they felt that the pieces were real with confidence. So we were past the confusion part and into the fooling them part, right? We also evaluated the enjoyment or the appeal of the music. We want the music to be beautiful. We don't want to create non-beautiful music, or all the bad words come to my mind, shitty, crappy, like that. So we want to produce good music. So we evaluated that, and most people liked the music. They felt it was good. It's not horrible. It's something they can listen to. We tried to see if there's a correlation between appeal and real synthetic, and they were really mixed up. So people were really mixing up the real with the synthetic along with the enjoyment. There was no clear distinction. The demo we saw, I hope the presentation will be available online a lot. So we have a website with the demos, the source codes, the pieces that we tested with, everything, with some links to some Google Forms that we used to perform the tests. You'll find all the pieces that we used for testing there, and the forms to fill in your inputs in terms of synthetic, real, the sentiments that you perceive. You're more than welcome to participate. The more we have results, the better we will be able to analyze and improve our system. So to conclude, why did we work on this? We mentioned those guys as a reason in our papers. Because when you're submitting a paper for publication or you're publishing something, you have to show that it has practical applications. But to tell you the truth, I didn't, and Ralph didn't work on this for these applications. We worked on it because we want to discover the nature of the human way of thinking. And we thought, okay, music is thought to be something specific to humans, very complicated. Let us dig in this area and see whether we can do it computationally. That was my personal and Ralph's personal motivation. I think we got somewhere. I think we were able to do some interesting things. Of course, a lot needs to be done. I think the time is over. Okay. A lot needs to be done. We have a lot of challenges still. I'm not going to go into a lot of them, but basically considering more features. We considered 7 features only. There's another 100 features that we can consider. Doing things more properly in terms of learning chords progressions, in terms of using, instead of using a fuzzy KNN, which is a very simple learner, using some more complicated learners, even though we're scared of the parameters. But it would be interesting to see what those can produce. And as a final idea, we were thinking, okay, if our guy can predict sentiments and can compose music to reflect those sentiments, can we teach it to simulate other composers? Like, can I give it a bunch of pieces composed by Mozart and ask it to learn Mozart's style and then compose as if it were Mozart? Can we reenact dead composers using this guy? This is a future step which we didn't start working with. It sounded scary when we were thinking about it, but based on what we're doing, it's not very far-fetched, okay? So I hope you enjoyed the talk, and at your disposal for any questions. Please, please. Jonathan, please.
I have a question. When we say a song is happy, or it's between happy and calm. Okay, when I perceive a song as happy, would he perceive it as happy as well? How did you deal with the fuzziness or the subjectiveness of this issue?
This is a problem with, thank you for the question, very important question. This is a problem which is common in learning, in machine learning. Whenever you want to train a system to learn things the way humans perceive them, we need inputs from humans. And humans don't always agree, right? This is a problem. Humans don't always agree, especially when it's artistic. Some people we had people perceive Silent Night as sad, while the majority perceived it as joyful and happy. So here, there should be some kind of a sampling. There should be some kind of a statistical study, which we did. We collected a lot of data, as much as we could, from our students, from graduates, from teachers. And then we did statistical analyses, identifying the averages, the standard deviations, the distributions of the data. And then we identified the outliers, people who, for example, rated Silent Night as sad or surprising, or those were outliers, 1 or 2 out of 100 maybe. And the outliers we filter out, and we keep the representative data distribution, and that's what we use to train the model. So the model is designed to get all of these inputs and train accordingly. But we have to be very cautious in terms of the data that we use for training. If the data is wrong, it'll train wrong. And then it'll produce results which are wrong. So there's a data cleaning, if you want to, or data analysis phase, which has to precede the training. We have to make sure that the data is proper. In other words, it's like teaching your child. If you teach it wrong, it'll learn wrong. We have to know what we are teaching the guy, and then we can evaluate accordingly.
Okay, thank you.
Thank you. Jonathan, yes.
That's okay, I'm loud. That's it. It kind of represents how all music is made to begin with. An artist just tries something, tests it out on their friends, and sees if it's nice. So you said at the beginning that you're not replacing humans as music creators, but I think what you've done is you replaced the piano with the computer. And so basically you and Ralph are the composers, and I'm asking you if you agree with this, the composers, and the AI is just your piano.
No, I would not agree very much. I'd say the software itself is the composer. We are the designers of the software. Like since we're talking about parents and children, it's like we're the parents and it's the child, but the child is composing, not the parents. The parents did their job in raising that child properly. But then the child is doing we cannot take credit for what it's doing. We take credit for our design of it. But then when it's composing on its own. We're not intervening in its composition. Now, the question on whether we are replacing humans or not, we had many discussions at LAU. We have Mr. Joseph Khalifi. I think you know him maybe. He's a composer, and we invited Jean-Marie Riesche, who's a national composer, and we discussed with many people who worked with us from the National Conservatory of Music and so forth. They were scared. They told us, you're pushing that boundary. You're pushing that boundary of replacing human composers. But some of them, like Jean-Marie Riesche, he said, okay, this could help us. Maybe it could give me inspiration. Maybe sometimes I lose inspiration. Maybe I could ask it, okay, compose something which reflects those sentiments. It composes something, and then I take it as an inspiration and I compose. Or maybe I start my composition and I ask it to complete it. He told us a lot of times I compose something, but then I'm lazy. I don't want to continue working on that anymore. I want to work on something new. So I give it the initial part, and then I let it compose and arrange, and it'll do it for me. So it could help, and it could replace. It depends on how we want to use it, like any technology. It depends on the usage later on. Yes. Maybe. To tell you the truth, right now, I'm working on other things, Ralph is working on other things. So for now, this is where we got. And we made everything available online, and we submitted for publication. So we want researchers around the world to know what we're working on. Whether we will personally continue the work, or whether others will pick up where we left, we're not sure yet. Because you need two to tango. Right now, my graduate student is not here, and I'm busy with other things. So at the time being, there are no plans. We are not working on it right now. This was completed in 2 months ago. In the summer of 2018. So I hope we or someone else can pick it up and continue from there.
I have 2 questions. The first one, did you try with several instruments at the same time?
No.
And the second question, suppose you let the application do a synthetic Mozart. Can you let the system know which is the right Mozart and the synthetic Mozart? Can it know by itself?
Concerning question 1, the piano is what you listen to and what I listen to. This is something that we understand as human beings. It doesn't need an instrument to understand the music. It composes by musical scores, the notes. It's like your Beethoven. Beethoven used to compose in his mind. He didn't need to listen to the music to know what he's composing. Likewise, we gave the pieces, the scores, to a pianist, and we asked him to play it so that we can understand the music. As non-experts. Oh, I know music, Ralph knows music, but people who test, they need to listen to the music. So we thought the piano is the most universal instrument. Now, timbre, which is the quality of the instrument, the way you distinguish a piano from a violin, this is called timbre. This is a feature for music analysis, which we didn't get into right now, because we're not focusing on the different instruments. So we thought we want to play with music. Let's keep the instrument-specific features outside of it right now, because it adds complexity, which we don't want to delve into at this stage. Regarding the Mozart synthetic versus, we're not there yet. As I told you, this is an idea of having it learn.
No, the question, can you be able to detect, if I forge Mozart, will you be able to detect that this is not the right Mozart?
I don't know. This is what I'm saying. We're not there yet.
Is that a possibility?
Why not? Why not? Right now, what we're doing is we're teaching it to recognize sentiments. We're not teaching it to recognize composers. We need to prepare the data properly to train it, and then we need to test and see, is it able to recognize, to distinguish, for example, between Mozart and Beethoven, and then Mozart and a synthetic Mozart. These are things which we didn't get into right now, but from a scientific point of view, I don't see why not. I don't see why not. Yes. Yes.
How do you judge the creativity of the composer versus it just, repeating the input data?
At this level, in terms of creativity, we basically, aside from non-expert users, listening to the music and rating whether it's real synthetic, which is a sign of creativity. Like, if they think it's synthetic, it means it's not creative. It means it's repetitive or it's machine-like. So there's that input. And then we gave it to 3 experts. One of them, the pianist who played the pieces. Another one, who's an instructor in the National Conservatory, and another who's Mr. Joseph Khalifi, our own LAU composer. So they listened to the pieces and they told us we made them listen to the pieces without telling them that it's, and then they weren't able to guess. They weren't able to guess.
I think what I meant is creativity in terms of originality.
Variation?
Yeah, not variation in the piece itself, but how different it is from the training data.
It is different from the training data because the pieces that were produced were really different from the training data. Because it's not composing by taking the original data and changing them. It's composing by starting with the basic notes. And it adds to the notes to form chords, and it adds to the chords more and more chords. So this is why we use the Evo-Devo genetic algorithm rather than the traditional genetic algorithm, which starts with a piece, and it starts changing it and flipping it around and mutating it. In that sense, you start from pieces, and then what you're going to get is a derivation of them. What we did is we composed from scratch, just like a composer composes things, by starting with notes, adding one note to the other, adding one note to the other, and getting to what it wants to get to. The genetic algorithm, what it does is, at every stage, it compares in terms of sentiment expressiveness. It compares the piece that it produced with the sentiment vectors of the training pieces. And then it simply judges whether, okay, this guy expresses the sentiments that we want to express or not. But that's the only thing it compares. So in that sense, now some of the pieces might have similar patterns. I made you listen to two or 3 or 4 pieces. You can tell it has a certain style of its own. But when you tweak the parameters a little bit, when we tell it, okay, use those mutations and not the other mutations, speed things up in terms of tempo, we can specify those. We can keep it open, free for it to choose, or we can tell it speed up the tempo. Use try, use staccato more than other mutations. And then it will produce pieces which are different. This part we need to work on. In other words, choosing different or optimizing the choices of the mutations, maybe, when it's composing, when it's adding those notes together to produce some bizarre things or strange things. But in our process, to make sure that the pieces which are produced are varied or are different from each other, in the genetic process, we have trimming based on variation. In other words, or variability. In other words, we don't want pieces to be repetitive within themselves and compared with other pieces. Here at this level, what we do is every piece, we have a population. Every piece that is chosen should be as different as possible from all the others. So the first candidate is different from all the others. The second candidate is different from the first. The third is different from the first and the second. In other words, we go with difference at this level. To choose, if we want 5 pieces, we choose the 5 pieces which are as different from each other as possible. So there's the sentiments and there's the variability or the differences to make sure that they are different from each other. But then again, a human composer also has a style. Like when you listen to Mozart, I'm a Mozart fan. You can identify Mozart. When you listen to 2, 3, 4 pieces of Mozart and I make you listen to another piece, you can tell this is Mozart. He has his own style. So it's not wrong for it to have its own style. But what does that style mean? Where did it come from? We need to look into that in more detail.
I know that the topic is super interesting and there are so many questions, but we can only accommodate one more, and then in the Q&A we can have more, the networking.
Thank you. Hi. Let's say the AI created a beautiful song, and it was really good, in top 3 on the Billboard.
Yes.
So who would take the rights to the song?
This is an interesting question. It's like the question of if an autonomous vehicle hits someone and kills someone, who's responsible? Is it the vehicle? Is it the owner of the vehicle? Is it the company who produced the vehicle? These are questions that are being discussed and debated right now in terms of the legality of things. If you want to start selling, or if you want to start doing business with these guys, who's the owner? I'm not a lawyer. I can't answer. I think the composers, he's the composer, but maybe the designers of the composer are yes, but then again, are the parents of a certain child, the proprietary, the people who own everything that the child produces? Will it have its own identity later on? Will AI have its own identity later on, which is distinct from the creator's identity? These are questions which are discussed at the legal level. Compose? I don't see why not. I'm telling you, this guy is available online. I invite Ramzi to check it out, see whether it's interesting, and keep us posted. And all the proceeds will go to research. It's not business. Ralph doesn't care about business. I don't care about business. I'm in academia because I don't care about business. I'm going to live for 20, 30 years, 40 years, 100. I don't want to waste my time running after money. So we don't care about that. Check it out. If it's interesting, get back to us, and we see how we can go from there. Thank you. Thank you.
Thank you so much, Dr. Te'le, for the super interesting presentation. Maybe we'll have a new Fairuz, AI Fairuz or something in the near future. Okay, so moving on with our last presenter. We're going to see AI in the medical field with Abdurrahman Ghalab. He's a data scientist currently, and he's going to share with us his application of AI in cancer detection.
Hey everyone. Yeah, so they were really interesting presentation that I had with Dr. Te'le and Ramzi. And now we're gonna see how AI is impacting another very important field. It's about using AI in medicine, especially in medical diagnosis. My name is Abdurrahman Ghalab. I work as a data scientist at Numbase Group, and my manager is here actually to test my skills, I guess. So first we're going to talk about how we are using AI in diagnosing melanoma. So first, melanoma is the most fatal and frequent type of skin cancer. It's usually caused by the long-term exposure to ultraviolet rays. The project of automating the diagnosis of melanoma started as a collaboration between the natural science and computer science departments at LAU. And actually it started while I was in my first year, and there was a lot of effort put in that project. Some people use pure image processing, some people use genetic algorithms and other AI techniques. However, here we start using deep learning, and we use different approaches, and we compare between the performance of different approaches in this problem. So first, about melanoma diagnosis. If someone has melanoma is like any other kind of tumor. It might be malignant or it might be benign. So malignant is the dangerous type of moles. It's the cancerous one. It's where you should actually worry if you have one. And the benign, that you should not really care about it. It's just it might be a freckle or something. However, for melanoma diagnosis, usually the manual process that you go to a dermatologist and you do some dermoscopy test. And this process is it doesn't take lots of time, yeah, but however, it's not really accurate. So after that, if they are not sure about the results, usually they do some kind of a biopsy. They take some sample of the skin and they test it whether you have cancer or not. However, this process is actually expensive and it takes lots of time. So our efforts to automate the melanoma diagnosis was actually to produce some model that is cheap and it can be user-friendly, put in a mobile phone. If you're suspecting that you might have something, then you can just grab your phone, scan it, and send it to the cloud, and the cloud will return to you whether you have a malignant tumor or a benign one. So here we are presenting two approaches. So the first approach, I use the traditional approach mentioned in research, where I take the images, I do some image processing, I extract the image of the tumor from the skin, then I extract some features, some visual and geometrical features. Visual like the shape and the irregularity of the borders, the asymmetry. It can also be the color variation. We will discuss them in details. And the next one, which was about using deep learning or computer vision, all those nice buzzwords, we're going to talk about them now more in a little bit of details. So the first approach, known as the ABCD rule, I will let you know why it's called like that. So the first approach, it has several steps. The first one is about data collection, data cleaning, and hair removal, because it's taken from the skin, so it might contain hair that is covering the tumor or like it's in the image. So I need to remove the hair using image processing. Then I need to segment the tumor, which is extracting the part of the skin that actually has a tumor. And also about feature extraction, the features we talked about, the asymmetry, the irregularity, border irregularity, the color, the diameter. And then we build some machine learning model or statistical model that, given those features, it would return to me whether this image corresponds to a malignant or a benign one. So first, talking about data cleaning. So since we're doing image processing, usually and most of the time we would need to do a manual inspection of all the images we have. So because you never know, images, they come from different sources, maybe they were not cleaned before, maybe you got some random images. So maybe the first image here, okay, that's a good one. That's a good one as well. Here actually it's like on part of the hands, and it would be really hard to automate the image processing to extract this mole, and it would be harder to extract some useful information from it. And this was just my dog's picture. It just sneaked in the folder, so make sure you don't add some irrelevant or useless pictures in your data. Then the hair removal. So we have this picture, and we have 3 hairs here, and we need to remove them. So we would be able to extract this area. So we automated that process by doing some morphological operation. And image processing, this is just that we are doing some restructuring to the pixel on the micro side, on the micro level. So I'm taking some group of pixels and I'm giving them a new shape. So what we see here, the hairs, they haven't totally disappeared, but now on the micro side, if you zoom in, we cannot really do it here, it would have a shape of a diamond. So here you can say that we distorted the image a little bit. Then the tumor segmentation. So here we applied some blurring to lose some of the useless data outside the tumor. Then we apply thresholding. Thresholding is a concept in image processing where we pick some value, some color value within the pixels, and I choose for each pixel, if it has maybe like a lighter color, give it maybe white. If it has a darker color, give it black. Just a thresholding process to split them into 2 classes of colors. Then here the result, we still have some undesired components or some parts of the image that we don't want to have. So what we did here, that we applied connected component filtering. We chose the biggest connected component in the image that is closest to the center. And here we got rid of the other details. Then we did the inversion just to keep the tumor side, the tumor part of the image, to keep it white, and the rest is black. And this was the final result. So we start from here. We managed to remove the hair. Then we managed to remove other details that we might include, and this was the result. And of course, we would have to do manual inspection. So because the image processing procedure, they are usually very error prone, so I have to get each image and its corresponding segmentation or result and compare if my segmentation was actually right or I screwed up somewhere. Then once we have this segmented image, we can actually apply feature extraction. The features we talked about: asymmetry, border irregularity, color variation, and diameter. Some researchers they use those features, some they use more features or less. It depends on some research in the medical field. However, we'd stick to those four. So asymmetry, because usually in the medical research, they believe that malignant tumors, they have some kind of, they are less symmetric. So what we did here, that we took the image, we took its reflection, then the intersection between them, and that was the result. And after that, we applied some mathematical equation about the diameter over the area over a mathematical equation that would just give me a value for the asymmetry, because I want to quantify, I want to convert the images into numbers. And for the border irregularity, we just apply two mathematical equations that would extract two features, with our circularity index and adjusted irregularity index. Also, we had the color variation and the diameter. So for the color variation, they are actually the malignant ones. They are known that they have like big difference or variation of the color of pixels. So we computed that as well. And the diameter, we just extracted the diameter of the circle that encloses or encircles the tumor. That was all just mathematical operation done on the images. And after we have done all of that, now we have our data. So for each image, we had the asymmetry value, circularity index, or adjusted irregularity, the diameter, the color, and their corresponding class. Now I have my data ready. I would just apply one operation, which is normalizing all the values. If you're interested or working technically in the field, you would know that normalizing, we do it so all features would matter the same amount. Then we apply tenfold cross-validation, which is also a technical term where we are splitting our data set into 10 groups, and I'm taking 9 groups per term, training on them and testing on one. Then once we have the data ready, we applied the different machine learning techniques. So you can see that we applied logistic regression, naive Bayes, random forest, key nearest neighbor, artificial neural network support vector machines. Those are, I'm building classifier models that I would give each one the data, the features for each image, and they will return to me whether this is malignant or benign. Of course, like the longest part was doing the image processing. However, this procedure as well, it didn't take lots of time. However, it took me some time to tune each model to pick the best value, the best parameters, so it would produce the highest accuracy. We recorded the results and we kept it aside. And now we move to the second approach. So the second approach is about using convolutional neural networks or computer vision or deep learning. So what's interesting about this, the whole tedious part about the image processing, we managed to eliminate it. We don't have to do a lot of hand engineering for the features. We don't have to extract them by image processing. This convolutional neural network, it can manage to learn the feature and extract the feature on its own. So this is an example from maybe like autonomous driving car. And this is a car, so the convolutional neural network is just an architecture, a procedure of some units, computing units, that would process each group of pixels in the images until it manages to learn spatially within the space and visually what a car means, what a truck means, what a van means. So it extracts the feature, then it manages to classify. Here we do feature learning, then we manage to classify. So you can say that here we just summarize the whole image processing part. This is another example from the Andrew NJ's course about computer vision, if you took the series. So here it's a task for maybe face detection or maybe face recognition. We see in the first few layers, we just extract some very simple features about the images. Maybe about the edges, how tilted they are. Then in some other layers, in advanced layers, we managed to learn that those group of edges, most probably they correspond to an eye, or maybe they correspond to a nose or something. And in advanced layers, we managed to learn that this group, maybe like nose and ears and blah, they correspond to that person that we're trying to recognize his face. So here in convolution neural networks, most of people, they don't reinvent the wheel. They just use other architectures of neural networks that they were used before by other researchers, produced by other researchers. So it's a very known concept, and especially in computer vision, it's called learning transfer. So some other scientists, they developed this architecture, maybe called Inception. They developed it, and they taught this machine, or this machine learning architecture managed to learn a lot of features in some task. So what I do, that I take the same network, I edit in the units, I change a little bit in the parameters, so it suits my problem. Then what I do, that I'm feeding it the networks, and I'm making the network. Maybe it was used in autonomous driving. I change it so it suits the problem of melanoma diagnosis. And the intuition behind that, in deep learning research, they believe in the all convolution neural networks. At early layers, they actually learn the same kind of parameters. They learn some kind of general parameters or general features that they are general to all images. So what we did here, that we used the learning that was done on those two networks. The first one was developed by researchers at Google, and the other one was improvement on it. So first about the Inception network. So they were inspired by the movie Inception, where in the movie it's layers of dream, and they go deeper in layers. And this is what they did actually in the Inception network, that there were some challenges in going deeper in layers in computer vision. So once they managed to overcome those challenges, they produced this paper, and they called it Going Deeper with Neural Networks. So this is why it has the name. And the Inception network, it was an improvement of the Inception network, and they just call it Extreme Inception. That's why. It was trained on some task for object detection or object recognition on 350 million images to categorize around 17,000 objects. So that's a huge amount of parameters. Now we have our data. We have the network. We tweaked the network a little bit. We added some units, removed some units. And now we have our data that we need to prepare. So in total, we had this amount of images, 13,791 of them malignant. You can see the numbers. So then we divided the data set into two groups. The first one, 80%, that we did tenfold cross-validation, the same one we did in the other approach. And we kept 20% of the data. We didn't train on tests on them unless we got the final results, so we would give like some kind of a final estimation. And this is the actual accuracy of our neural network, regardless of the training and the testing. And also, if you're interested, since we get our data from different sources, we had to rescale all the images. So maybe like some of them would be high resolution, low resolution. So we scaled all of them to that one, 299 times itself, times the 3, since we have 3 channels RGB. And all images were normalized by dividing over 255, for the same reason we mentioned before in the approach one, because we want all the values to range from 0 to 1. One last step in data preparation, which is called data augmentation. And we applied that because in computer vision or machine learning, we have a problem called model overfitting. The model overfitting is that your model only succeeds on the data that you have trained it on. However, once you get a new data from the world, it fails. And this can be due to many reasons. It can be due to technical reasons. It can be due to that your data is not enough. So what we did here, that we were just getting each image and we're changing it a little bit randomly. So it's as if we're adding variety to our data. So maybe this is the original image. I did some random rotation on each image. So maybe I would feed this data to the network during training, or this one, which is rotation by 90, or 270, or 180 degrees. I'm doing, maybe you can say, random augmentation to the data every time, so I'm giving the data, my model new data. However, if you're working in computer vision, you know that there are other augmentation techniques, which we can do random cropping of the image, so maybe it would not include all the tumor, it would only include part of it, which might correspond to some problem in real life. Not all images, they include the full tumor. So maybe we'd not be able to extract some features. So we do random cropping. However, we didn't do that here because since it's random, it might add some noise by adding images that doesn't even have the tumor. So it's not like something that you should follow. It's some kind of a problem-specific augmentation. So the results, we applied the first approach, we applied the second approach, we get the results. However, before we move to the results actually, let's keep in mind some notes while you're carrying out some machine learning problem, some machine learning experiment. So first, keep in mind what's your goal, because usually we start with some goal in machine learning, then we find out that, okay, it's not even possible to solve it using machine learning. Or maybe we would know, okay, yeah, maybe I can do that and I can do more actually with the data I have. However, it's not advised to go into different peripheral problems to solve them while you are doing one. Maybe I started the project when I wanted to classify them into malignant or benign. Some other stuff I can do with the same data, I can actually give the patient and tell him this malignant tumor is in that stage, and maybe this is a hopeless case or not hopeless case. Maybe you need to do some surgery. I don't know. Maybe we can do that. However, just focus on the main goal, and once you finish it, just move on to the next one. Also, what's your problem-specific goal? So in each problem, there is a specific goal. So maybe in the problem of melanoma diagnosis, maybe we can produce a model that gives me 90–80% accuracy. However, it tells most of the users that they don't have cancer, although they do have cancer. So it's a high accuracy. However, maybe because I don't have data of lots of people who have cancer, it gave me actually bad results. And so it's actually a paradox, whether you should you tell them that you have cancer while they don't, or should you tell him that you don't have cancer while they do? So you have to have a specific goal. Most of the problems when it comes to medicine, they usually take the safe side, and usually they give them, if they are suspicious, usually they give them positive results. They tell them, okay, we're not sure, but most probably you might have. Maybe the patient will go and will go again to a dermatologist or do more research about his case. However, usually people in the medical field, they stick to the safe side. So when carrying out a machine learning experiment as well, usually don't take the first set of results, because it's a really tedious problem. You be working on the image processing and repeating and repeating and repeating. And it's all because it's an iterative process. So don't take the first set of results and say, okay, I got 80% accuracy. Maybe you can do better. Maybe you can change a little bit in your model. Maybe you can use a different technique during the image processing. It's an iterative process. Also, all real-life problems, they are beyond the data that we have. So maybe if you're working on a similar problem, and all the data that you've got, they came from people with light color skin. And then someone came with dark color skin, and maybe they are testing, most probably it would fail. So maybe be a little bit specific and know what your data is about, and mention that to other people as a disclaimer. This data was trained on people who have light color skin. yeah, so be prepared to get disappointed. There is no model that would do 100% or would solve all problems. Okay, now actually the results. So when we applied CNNs or computer vision deep learning on big data sets, it managed actually to learn features on its own and give robust models that give higher accuracy. Actually higher accuracy than the dermatologist level. There is a paper published by Stanford that they actually gave some images to dermatologists and they measured their accuracy. So the average accuracy of a dermatologist, it's 75%. The accuracy we got here, it was around 88%. So that was because CNNs, we managed to eliminate the part where we do image processing, the hand engineering for the features, and it managed to learn features on its own. And we managed to add variety to it. So if new data came, it managed actually to generalize and would give results that would be accurate. So conclusion, CNNs, they are robust models, even to outliers. So if you had an image that is totally an outlier to your data set, most probably it managed to classify it correctly. And as we said, it's related to the problem that you have, the specific goal. So our specific goal is to give higher positive rate. If someone has cancer, tell him that you have cancer and be on the safe side, even if it might hurt the overall accuracy. So the results when it came to deep learning, it managed actually to give a true positive rate. It managed to tell most of the people who had cancer that they really had cancer without hurting the overall accuracy. And as we said, it managed to outperform the dermatologist level classification. Here's a little bit of detail about the exception architecture, which managed actually to learn stronger features than the inception and managed to produce a higher true positive rate. So final thoughts. So I started the project with the goal of obtaining a higher accuracy than the one mentioned in literature. However, once I started working in that, I thought about it. Maybe I can get I can get some data and I can do the image processing, repeat the same process that was mentioned in literature, maybe improve on the results. And it did improve in the results on the same data. With a little bit tweaking, with a little bit changing in the models, you can produce higher accuracies. Within each approach, we compared between the first approach per se, the one we use image processing, we compared between different machine learning approaches, different image processing approaches, and within approach 2, where we use deep learning, we managed to compare between the different architectures, the different parameters that we gave, because like in deep learning, you have a lot of parameters that you have to change, or you have actually to fine tune. And because we have to record all of the for future work, if you're working with similar problems, you better keep this data, because mostly when you're doing machine learning problem, usually you're just like the machine that you're dealing with. You only learn from the bad data that you have got, or the bad results that you have got. Thank you. Questions?
Them to have equal weight. Why would the color have equal weight as asymmetry? Why not one would be a higher weight?
Okay. So the problem actually with normalization, we can look back at the data here. I meant actually to leave a screenshot here. If you can see the diameter values, they range maybe from 3 till 10, 20, they are in millimeters. And the A value, usually because it's an index, so usually it's from 0 to 1. And here they have a much higher difference. So if you are measuring how this one, how maybe like the circularity index or each one is impacting whether this patient has cancer or not, if you have this, most probably the adjusted irregularity index would take most of the parameters because they have higher variance or standard deviation. Does that answer
you
your question?
decided all the factors would have equal impact. Yeah, the color would have the equal impact as a diameter. Or
It's not like it would have equal impact, but then I feed it to the model like that, and then the model I feed them like all of them. They have a standard deviation of 1. It depends. Like if it's between -1 and 1, they would have standard deviation of 1 and mean of 0. So then the model can actually give more importance to each one, but I cannot give the data where there is very high standard deviation between the different features. No, they actually come from different sources. So what we had to resize them. So all of them, they would have the same size we are feeding to the network.
But does the pixels affect the results, the megapixel inside the image? For example, if one image was shot in a professional camera and another one was shot with a simple mobile phone, doesn't that affect the results? The pixel difference.
It would usually affect about like the quality that we're talking about, how many pixels within those frames. So we're restricting them to 299 times 299 number of pixels. Okay. So the quality thing, it's about how many pixels are representing this area in the image. So you're just giving them that every image would have this number of pixels.
And you combine the two approaches, deep learning and the first approach and the second approach in the same model, or two different models?
No, they are two different approaches, and each approach it had many different models or techniques. Yeah, please.
Which API were you using? Were you using TensorFlow, PyTorch?
So for the first approach, it was pure Python. I didn't use TensorFlow. I just used for the image processing. I used CV OpenCV, Open Computer Vision Library, and for the learning, I used sklearn. However, for the deep learning, I used TensorFlow.
Why did you use TensorFlow? Was it random, or did you compare the APIs and you chose it for a certain reason?
Actually, by that time, there were not a lot of. That was like 2 years ago, and there were not. Now we have PyTorch. We have another one which is Keras that is based on the back end on TensorFlow. However, like usually it doesn't really matter. Maybe it would matter a little bit on the computational efficiency. But it would not really matter how good the model is learning or not. And TensorFlow is actually the most used library or framework for that, for deep learning. Thank you. I'm sorry? Can you talk?
That you use?
No, can you talk?
Can you go back to the slide? Outperform. Oh. Yeah, you mentioned when applied on big data sets, CNN outperformed traditionally technique. What are the countermeasures that you use?
What is? To measure what? I'm sorry. You mean the metrics that you've used?
You have a problem. Outperformed. It's not a problem for you.
No, it's not a problem actually. It's an advantage that outperformed, like it performed better than, yeah. So if you're asking about the metrics that I have used, so I use the overall accuracy of the model.
I think that you use a big data set that you are over learning the machine. And if you use too much image, that means you are over-learning the model, and finally you will find yourself stuck.
This is the problem that we discussed about model overfitting. But however, it's not produced once we have lots of data. Actually in computer vision or in deep learning, it manages It overcomes the problem of overfitting by having lots of data and having variety of data. Because the overfitting, that your model only performs well on the data set that you have. So once you give a bigger data set, it would be actually a better one.
Okay, any more questions? Yeah.
Okay, I didn't actually replace the hair. I managed by doing morphological operation and I am doing blurring. When I did the thresholding, so all the other details that didn't include the tumor, they were just erased from the data. All right.
Okay, thank you. Okay, one last question.
So the first approach, it took actually lots of time to do the image processing because I tried different techniques in the image processing and measured which one managed to keep most of the info in the data. However, for the learning part, it was maybe like a day or something for all of them because you have the features and it was not a really huge data set. So it didn't really take much time. Maybe it took a little bit of time tuning different models. However, for the second approach, the problem was actually with the experimentation, because before I used Amazon Web Service, it used to take around 2 weeks to do one experiment, the 10-fold cross-validation. And I did many experiments of them. So I was doing that on a 16 gig RAM and 3.2 processor, and it was taking 2 weeks, 24/7. Yeah.
Thank you so much for the very nice information. So thank you all for attending. We hope you enjoyed it. Our event is not over yet. We still have the networking session where you can share more questions with the speakers. And thank you for coming.